In this section, we're still talking about vectors, but we're going to move away from vectors that have scalar components to now vectors that have function components. And these are called vector-valued functions, and they form curves in space. So typically, we would write a vector-valued function as r of t, and instead of having components r1, r2, r3, this vector is going to have functions as its x, y, and z components. And these functions are all going to be functions of t, which makes our overall vector-valued function also a function of t. So it's just a vector that has functions as components. The most basic type of vector-valued function is a line in space. So in order to write the equation for a line in algebra class, we had to have the slope and a point on the line. Well, slope in three-dimensional space would be equivalent to having a direction vector. The components for a direction vector describe how our coordinates are changing in the x, y, and z directions. So we would have this direction vector we call v. And we would know the components for v. Let's say they're a, b, c. We would also need to know a point on this line, and we'll call that p. And it has coordinates x1, y1, z1. So what's unique about a line in space is that if we pick any other random point on this line, which we'll call Q, the vector that we create between P and Q should be parallel to vector V. And we don't know what Q is. We're trying to come up with a generic representation for every point on this line, so we're just going to use variables x, y, z to represent point Q. So PQ is parallel to V. And what that means is that the components for PQ and V are scalar multiples of one another. So if we create vector PQ, we're going to do the Q coordinates minus the P coordinates. You always do terminal minus initial. We're going to have x minus x1, y minus y1, and z minus z1. So these components should be scalar multiples of a, b, c. And for our scalar multiple, we're going to use the variable t. So we're going to say a times t, that's the x component for v, should be x minus x1. So a is a scalar multiple of x minus x1. And we need to use the scalar multiple for every single component pair that we do. Back when we checked for parallel vectors a few sections ago, we said if any of those ratios came out different, then it wasn't parallel. So we need to make sure that we're using the same ratio of t every time. So bt is equal to y minus y1, and ct is equal to z minus z1. So if we were to solve these equations for x, y, and z, we would get a vector-valued function, r of t, which has components a times t plus x1, b times t plus y1, and c times t plus z1. So this is a vector notation for a line in space. We could also write them as a pair of a set of parametric equations. And that's just when we pull each of those out and identify them individually. So we would have x of t equals at plus x sub 1, y of t equals b times t plus y of 1, and z of t equals c times t plus z sub 1. So you see it's the exact same thing we have here. We're just identifying them individually when we write them as parametric equations. So let's see exactly how this equation works. We are going to find the vector valued function for the line that passes through the point, and we're going to call this our P, 2, -1, 4, in the direction of V, which has components, (3, -2, -1). So we don't have to every single time work this out by doing creating a PQ and then setting up a ratio with V. We could just jump straight to the formula. But just to help you get a handle on that formula, I'm still going to work it out with the ratios. So we just pick a generic point Q, which we're going to force it to be on the line. We're going to create vector PQ. So I'm going to have x minus 2, y plus 1, z minus 4. And PQ, since P and Q are both on the line, PQ must be on the line. We know V is also pointing in the same direction as the line, which means these two vectors must be parallel. So they must be, all those components, when we set them up as a ratio, must have the same ratio value, which we're going to call T. So 3 times T must equal x minus 2. -2 times T has to equal y plus 1. And then -1 times T has to equal z minus 4. And if we solve this for x, y, z, we will have the components for our vector valued function, which is 3t plus 2, because we're solving for x, -2t minus 1, and -t plus 4. The 3, -2, and -1 came from our direction vector, and then we got the -2 plus 1 minus 4 because we created a vector between P and Q, and when we do that, we do the Q components minus the P components, and we're using 2 as our common ratio. Let's try another one. This one's a little bit different. We are going to find parametric equations for the line that passes through the points, (5, 0, -1, and 2, 3, 0. So we're given different information this time, but it's still enough information to figure out the parametric equations for the line. The two most basic pieces of information that we need are a point on the line, and we've got 2 of them, so we're all set with that. And then we also need a direction vector, a vector that points in the exact same direction as our line. But since we have 2 points on the line, we can create a vector between those 2 points and use it as our direction vector. So we can call this, I'm just going to call it R and S. And our direction vector, I'm going to make by calculating vector RS. So we're going to do the S components minus the R components. 2 minus 5 is -3. 3 minus 0 is 3. And 0 minus -1 is +1. If both of those points are on the line, then the vector that we create using them will point in the same direction as our line, and we can use it as our direction vector. And then now we could use either one of those points, R or S, to set up our parametric equations. And I'm not going to go through the whole common ratio with t here. I'm going to jump straight to the answer, because the pattern that we see in the setup of these equations is exactly the same every time. We always have these coefficients come from the components of our direction vector, and then these constants come from the point that we're using on the line. So as parametric equations, we would have x of t equals negative 3t, and then you have to decide whether you're going to use r or s. So we could either say plus 5 or plus 2, but you have to pick one and be consistent and use that same point every time. So I've used 5, which means I'm using r, so all of the rest of them have to use r as well. So y of t is going to be positive 3t plus 0, and then z of t is just 1t minus 1. Now we also could have used point S, and our answer would look completely different, but it would still be the same line. So that's one important thing to point out here, is that the equation for a line in space is not unique. It's possible to come up with many, many different representations that once graphed all make the same exact line. Part of what dictates the fact that these three parametric equations are going to create a line in space is the fact that they are all linear equations. They all have t to the power of 1. So linear components create a line. But we're not limited to just linear components. We can have any type of function we want in there, and our curve in space will take on a similar shape to the types of functions that we see in the components. So in general, a curve in space, which a line in space is a special type of curve, it's just a straight line. We really could have a something that truly does curve, and the setup is exactly the same. We're just not restricted to linear functions for these components. So it's still a vector-valued function where each of our components is a function of t, but they are not necessarily linear. We could have quadratic functions or trig functions, square root functions, rational functions, and our curve that this vector-valued function creates would behave similarly to the functions that it's composed of. Because we're now not limited to specific types of functions, one thing that we need to address is the domain for our vector-valued function. We want to make sure that we're only plugging in values of t that will give us back a real number answer for each of our components. So when we calculate the domain for a vector-valued function, we really have to calculate the domain of each of those component functions individually. And then we need to see where those three individual domains intersect. To do those, to calculate their domains, we just need to think back to precalculus algebra and how we calculated domain in precalculus algebra. So there are certain types of functions that we learned about in algebra where the domain needed to be restricted. And now that we also have taken trigonometry, there's a few trigonometric functions as well. So one of the types of functions that we learn in algebra that has a domain restriction are roots with even indices, so like a square root. Or a fourth root or an eighth root. We cannot take the square root of a negative number. So what we need to keep in mind here, if we have a component function with a square root, is we need to make sure that whatever expression is under that root, which we call the radicand, is always positive. Another issue we come across is rational functions. And with rational functions, we see a component that has a fraction with a variable in the denominator. So like 1 over f of t. And we need to make sure that f of t is never 0 because it's in the denominator and we're not allowed to divide by 0. Logarithmic functions also have restrictions. If you think about what the graph of a logarithmic function looks like, it is only on the right-hand side of the graph where x is positive. And if this is something that you don't remember, you can check in your calculator and see if you try to ask your calculator what the log of a negative number is, it will give you an error. We also can't use 0 inside of a log. The log of 0 does not exist either. And there are some trig functions as well that have asymptotes, such as tangent, cotangent, secant, and cosecant. All 4 of those trig functions have asymptotes at different places. The sine and cosine function don't have any problems. They're just that one continuous wave that goes on forever. But those 4 trig functions, we do have to adjust our domain. These curves in space also have something called an orientation. Since they're represented by vector-valued functions, remember that vectors always have to have a direction associated with them. So if we were to have a vector-valued function with components for cosine t, for sine t, we can draw this vector-valued function by picking values for t and calculating what the x and y values are that go with it. Since my t is inside of a trig function, I'm going to pick some values that it's easy to take sine and cosine of. So if t is 0, we're going to get an x value of 4 and a y value of 0. So our first point is there on the x-axis. If we plug in t equals pi over 2, we get x equals 0, y equals 4. So we're up here on the positive y-axis. So as t gets larger, we are moving in a counterclockwise direction. And we can continue this. For pi, we'd get negative 4, 0. For 3 pi over 2, we'd get 0, negative 4. And then at 2 pi, we'd be back to the start. So what this is actually forming is a circle with a radius of 4. And we're moving around this circle in the counterclockwise direction. And when we draw this curve, since we know it's represented by a vector-valued function, we need to indicate in which direction the t values are getting larger. So in general, that is what orientation means. It's the direction that the points move as t gets larger. Let's try to find the domain of the vector valued function r of t equals negative t squared 2 over t plus 1 and the square root of 3 minus t minus 3. Let's say 3 minus t. So we want to know the domain. We want to know what kind of values are we allowed to plug in for t into this function. So what we need to do is we need to evaluate these three component functions for their domain individually. Negative t squared is a polynomial, so its domain is all real numbers. 2 over t plus 1 is a rational function, and since we have a variable in our denominator, we need to make sure that the denominator never equals 0 because we are not allowed to divide by 0. So if we set up that equation there, t plus 1 can equal 0, and solve it, we see that t cannot equal negative 1. So that's something we need to keep in mind. That's not our final answer, but I'm boxing it because we need to remember it for the end. Our third function, square root of 3 minus t, because it's a square root, we need to make sure that 3 minus t is always greater than or equal to 0. And if we solve that for t, we get that t must be less than or equal to 3. So we've got two conditions here that we need to meet. And one of the best ways to figure out where those overlap is to draw all of these on a number line. So I'm going to graph all three of these domains on the same number line, but I am going to shade them with different colors so it's easier to see where they overlap. So the first one we did was the domain for negative t squared, and we said that was all real numbers. We're allowed to use everything for negative t squared. Our second vector valued function was 2 over t plus 1, and we determined that we could use anything we wanted for t except for negative 1. So we've got this open circle at negative 1 because we're not allowed to use it, but we are allowed to use everything else above and below. And then our final vector valued component was the square root of 3 minus t. And we determined that this one was only allowed to use t values less than or equal to 3. So we've got a colored in circle at 3, and we're only allowed to use values that are less than it. Oops. So when we have all three of these graphed together on one number line, we only want to use the section that got colored all 3 times, because those are the sections with t values where all 3 of our component functions are defined. So the domain for r, well, all of this right here got colored twice. So that would be negative infinity to negative 1. But because there's an open circle on negative 1, we can't use negative 1. And then this section here got colored twice as well. And that section goes from negative 1 to 3. And 3 is a colored in circle, so we can put a bracket on that. And then this section we can't use because it was not shaded blue. So it couldn't be used for our third component function. So the 2 sections that we have that got colored all 3 times for all 3 component functions were the t values from negative infinity to negative 1, and then negative 1 to positive 3. The last topic for this section, we're going to start talking about some calculus for these vector valued functions. What we've done so far was graphing and domain, and that's all algebraic aspects of our vector valued functions. And now here at the end of this section and for the next couple sections, we're going to talk about some of the calculus aspects. If you remember back in Calculus 1, we begin our learning in Calculus 1 with limits. So we can also do limits for these vector valued functions, and we just work limits component-wise. So if you're asked for the limit as t approaches some value a for your vector valued function, well, if that r of t vector valued function has components x of t, y of t, z of t, all we have to do is take the limit of each of them individually. So the limit as t approaches a for the x component, and then the limit as t approaches a for the y component, and the limit as t approaches a for our z components. So it's really just 3 problems in one. And our vector valued function is continuous when our vector valued function has a real answer limit for each of the components. And it's equal to whatever we would get by just plugging a in to the function. So it's when r of a is equal to the limit as t approaches a for r of t. This means that our limits can be calculated with direct substitution. We don't have to use any fancy rules like L'Hopital's rule or factoring and canceling, any issues like that. We can get these limits just by directly plugging the a value in for t. So one more quick example. Let's suppose r of t is a vector valued function and it has components natural log of t minus 1, t cubed plus t, and negative t plus 5. We want to calculate the limit as t approaches 2 for this vector valued function, which really means we just need to calculate the limit as t approaches 2 for each of our component functions. And in Calculus 1, when we first start learning about limits, we always say that you should try direct substitution first. Just try to plug 2 in to your functions and see if you get any issues. If any issues arise, then that's going to be a point where our vector valued function is discontinuous and either the limit doesn't exist or we have to use one of our special rules to fix it. For this one though, if we just plug t equals 2 in, 2 minus 1 is 1 and the natural log of 1 is 0. 2 cubed is 8. Plus 2 more is 10, and then negative 2 plus 5 is 3. So we are able to calculate this limit with direct substitution. That means that r of t is continuous at t equals 2. And just in general, we're going to use the same r of t, and we want to describe the continuity. So we're not being asked to calculate the limit at any one specific value, but we just want to discuss in general what t values we are and are not allowed to plug in. Very similar to what we're asked to do when we calculate domain. So we need to look at these component functions individually, just like we did with domain, and we need to think about where we could run into some trouble. So for natural log of t minus 1, which is our first component, we're only allowed to take the natural log of values that are greater than 1. So t minus 0. T minus 1 must be greater than or 0. And if we solve that, we get that t must be greater than 1. If we were to try to plug a t value less than 1 into this component function, we would have an undefined x coordinate. We would have a problem. Our second component function is t cubed plus t. This is a polynomial, so t can be anything that we want it to be. So t is any real number. And then our third component function is negative t plus 5, which is again a polynomial. More specifically, it's a linear polynomial. So linear equations have no restrictions either. They're continuous for all values of t. So the only thing we need to worry about is what's going on with that first component. And if we want to make sure that our vector valued function r of t is always continuous and we're always able to calculate that limit with direct substitution, then we need to stick with t values greater than 1. Since this was this question specifically said describe, what I'm going to do is I'm just going to write out a sentence. It's not like an equation or a number answer, it's a statement since we were asked to describe. So r of t is continuous for all real numbers greater than 1. Since this was the only restriction we found within our components. If your restrictions are stated as values t cannot be equal, then you can also, instead of describing where it is continuous, you can also describe where it's discontinuous. So it would also be acceptable to say that our vector valued function r of t is discontinuous for all real numbers less than or equal to 1. That would be equivalent and perfectly acceptable.